Hello everyone. In this video, we are going to cover A5 relativity. So relativity is a chapter, is an actual chapter, and we are going to cover this topic in two parts. So in the first part, we will discover some basics of relativity and how to apply them. And in the second part, we will talk about space-time diagrams. Okay. So relativity is a kind of a chapter which is very non-intuitive because our intuitions are based on real-life examples. Here, the examples are set in extreme conditions where laws of physics does not obey as we want. Okay, there are some modifications needed, and this is where the relativity comes into place. So we'll start with very simple example. Okay, so there is a person in a train which has a scale and a clock to measure distance and time. Similarly, there is a person who is rest on a platform or a ground, we can say. He also have a scale and a clock. Now both clocks were synchronized at the beginning of the journey. Okay. Now once the journey started, the train starts moving with velocity v. So v is the velocity of the moving train, and we will name both these frames as S, which is a rest frame, and S dash frame, that is a moving frame. Now we will first like to define what is a frame of reference or reference frame. So it is a set of clocks and coordinates to measure time and position of an event. It is the exact definition you need to remember because they are going to ask this kind of a definition, okay, for 1 mark. So it is a set of clocks and coordinates that you need to measure time and position for an event, okay. Now, once we have two of those observers set into a motion, imagine their clock starts as they're ticking, and after some time t, some event happened. Okay. Now both are going to measure at what time the event happened and where the event happened. Okay. We are going to stick with only one-dimensional motion in this particular chapter. Okay. So just consider a simple linear motion. So this person, in the train, with his scale measures the position of the event as x dash as a coordinate and t dash as a time coordinate. Similarly, the person on the ground measures x and t as the time and position of the event. Okay. Now, according to Galilean transformation, it can be Galilean transformation or it can be Newtonian transformation. Okay. According to Galilean transformation, we can relate those two coordinate systems by a value that is v times t. Now, v times t represents the distance covered by the train in time t. Okay, so you will see that we can easily relate those two lengths. So the first is this, where the x dash can be given as x minus vt and t dash is going to be same. So we can see that both the frames will measure same time. Okay, the time will run similar or same, exact same for both of them. Okay, and we can, if x and t is given, then we can find x dash and t dash, and similarly if x dash and t dash is given, we can find x coordinate and t coordinate by using similar relationship. So this, until this point, everything makes sense. Everything is, say, simple Galilean transformation. The Galilean transformation is something that we use in regular kinematics as well in case of relative motion. Okay, so just to give an example, imagine a car is moving, like yourself is moving at 30 kilometers per hour and a car next to you is moving at 50 kilometers per hour. So as the speed of the car next to you, according to your perspective, will be 50 minus 30, 20 kilometers per hour. So we subtract whenever we find trying to find the velocity. So this can be also be done in Galilean transformation. And let's say the event is such that there is some kind of a ball or object moving. Okay, so let this be a ball moving to the right, and it has a velocity u and u dash. So u and u dash are the velocities measured by both the frames. Okay, so u is the velocity measured by s frame, while u dash is the velocity measured by s dash. Now, and we can relate those velocities. The person in the train will measure u dash. So according to him, it will be the object is going slower. While for the person in the train, for him, the speed of the object will be u dash plus v. So the speed of the object plus the speed of the train. Okay. So these are the relationship like Galilean transformation is very useful, and we use it on regular basis. We get correct, accurate answers as well. Now, two assumptions on in Galilean transformation that can be violated in certain conditions. The first assumption is that the time is same for all inertial frames. Okay. Now, what is the inertial frame? Inertial frame is a non-accelerating frame. Okay. So, so any frame that is moving with a constant speed or is stationary can be taken as inertial frame. And in this chapter, we are only going to deal with inertial frames only. Okay. The second assumption is that was that there is no upper limit to speed of light. Like speed of light uh, is more important because here speed of light wasn't discovered during the times of Galilean and Newtonian period, but there were a lot of experiments were going on, and nobody has an idea whether there will be a upper limit to speed of light. And then once we discovered the speed of light by doing some experiments, then we did multiple scenarios where we can change the speed of light. But in none of those experiments at any instant there was no where the speed of light was exceeded than the upper limit that we call as c. So c is 3 into 10 raised to 8 meter per second. So there is nothing at no situation where the speed of light were exceeded. So this is something that violates some of the rules. Okay, just to give you how the violation works. So imagine instead of a ball there is a photon. Now this photon is already moving at, let's say, u dash is equal to c as per measured by him. Okay, and if the train itself is going at speed of 0.5 c, according to the person on the ground, u dash plus v gives you 1.5 c. Now this number is a problematic. Okay, this number tells that we can exceed the speed of light, but which is not true. Okay, so this is where the Galilean transformation fails. So to improve on this, we Einstein came up with the ideas that built a foundation for the special relativity. Okay, and then we developed the maths of it. So as I mentioned earlier, inertial frames are the frames, okay, which are stationary or moving at a constant speed. Then we will talk about the two postulates. Now there is also another question based on the postulates of the relativity. So first postulate is all speed of light in all inertial frame remains same. So whether a person in the train is measuring the speed of light or person on the ground, no matter what the speed the train is going, the speed of the photon will always be c. That is the maximum length 3 into 10 raised to 8, unless a photon travels through a medium. Whenever a light goes through medium, refraction, dispersion, all those phenomena happens where a photon or light can get slowed down. But we are talking about all the situations. We are talking about air or vacuum. Okay. The second postulate is that all the laws of physics in all inertial frames remains same. Okay. So these are the two important laws, and based on this, we developed the maths of relativity. where we can transform or change these Galilean transformation equations, okay, into something that we call as Lorentz transformation. Now, Lorentz transformation derivation is not at all needed. Like how those equations came into existence. Some of those equations are given in data booklet as well. So we just need to know that, okay, we using those postulates, we can mathematically build Lorentz transformation or the modification in those equations, okay? But the derivation is not being asked. So imagine you have given v, x, and t. If these variables are given, then we can determine the x dash variable like x minus vt. It is same as Galilean transformation, like x dash is x minus vt, but here there is a gamma factor. This is a gamma factor. Okay, so x dash will be gamma times x minus vt, or if they have given you x dash and t dash, then we can have x dash plus vt dash. So there is a plus from minus, it will change to plus, and the gamma factor remains the same. Okay, the t dash is the scenario where we will get t dash. The time is not same according to Galilean Lorentz transformation. So t is the time in the original frame, and x is the coordinate position in the original frame. So x t minus xv upon c square into gamma factor. So that is the formula. Again, we can have, if t dash and x dash is given, we can use that to find t as well. So what is this gamma factor? This gamma factor is nothing but 1 over root of 1 minus v square by c square. Now, in most of the scenario, you will find that the v is given in terms of c only. So whenever you square it, the c square also get cancelled. Okay, and gamma, since v is less than c, gamma factor you will always find it is greater than 1. Okay, the in regular scenarios like a car moving on a road, the speed or the velocity is too much less than the speed of light. In that case, the gamma factor will be equated to 1. And if the gamma factor is equal to 1, we can easily see that this terms automatically converts into Galilean transformations. Okay, so these are the modifications that are needed. So when v is smaller than too much smaller than c, we get the Galilean transformation back, which is correct also. Okay, then regarding the velocities also, we measured u dash to be u minus v and u as v, u dash plus v. So we can use the addition of velocity formulas as well. Okay, so these are the formulas: u minus v over 1 minus uv on c square. These are velocities, so do mind the directions. Okay, but if you look at those equations, these are something that we need to remember as well. Because not everything is given in data booklet. Half of those equations are given in data booklet. So we should refer or get used to with those equations. Then most of the time we don't rely on just a position and a time of a single event. We mostly, all the experiments are dependent on two time interval, like two time instances or two events. Okay, so let's say if I have a and b as the points x1 t1 and x2 t2, then the distance between those events is given as delta x is equal to x2 minus x1. There is a distance between two events, and this is delta t, that is t2 minus t1. That is a time interval. Okay, so we can modify the Lorentz transformation. It won't be like any new term. It's just that the old terms will be replaced. So x dash will be replaced by delta x dash, and t dash will be replaced by delta t dash. Okay, and everything remains the same. Okay, so this is much more useful, Lorentz transformation, in terms of delta x and delta t, because most of the time we are dealing with the distances and time interval. The space-time interval is a very special quantity. It is a mathematical expression that is invariant in this frame of reference. What do we mean by invariant? Invariant means that if we calculate this quantity for a given for one frame, that quantity will remain same in the another frame as well. So what is this quantity? So this is delta S square is the space-time interval. Okay. So space-time interval relationship is given as C delta T the whole square minus delta X square. Okay. So this is calculated in S frame. In S dash frame, it will be very much similar looking. It is just T dash and delta X dash. And according to space-time interval, these two quantities must be same. The outcome of those equations builds a very unique equation that is very helpful in most of the scenarios. So C delta T square minus delta X square should be equal to C delta T dash square minus delta X dash square. Here we need to know that if four quantities are there, four variables are there, out of these, any three were given, we can figure out the fourth one as well. Now we will talk about few important phenomena of relativity. So one of those is time dilation. So time dilation is very important phenomena. So we will, in a train experiment, we will talk about one of the simple events. So a person in a train sees that a ball goes up from a certain position and return back. Okay. So he measures with his stopwatch, he measures how much time for the ball it took to go up and come back down. The displacement here, you will see that it is 0 because it has came back to initial position. So event 2 and event 1 are happening at same position. So event 1 is launching, event 2 is getting it back on the pad. Okay, but for the person on the ground, this event is not happening at the same position. Okay, you can see that the ball, as the train moves to the right, the ball also moves to the right, hits the upper part and then came back. Okay, so delta T will be equal to capital T. Let that we are just labeling it. So delta T dash is T naught and delta T is T. And if I use our transformation equation, Lorentz transformation equation, then delta T will be written as T, and delta T dash is written as T naught. Delta X dash is equal to 0. So we will get our equation, that is delta T is equal to gamma times T naught. Now this is a very important equation because T naught is a proper time, we are labeling it, and the capital T is dilated time. This is dilated because gamma factor is always greater than 1. So the other person in the ground will measure little bit extra time. Now how do we define proper time? Now defining proper time is very simple and straightforward. The proper time is the time interval measured by an observer for whom the events are happening at the same position. Okay, so here you can see that the person in the train, for him the events are happening at the same position, so he will measure a proper time. Okay, so this is the definition of proper time. So proper time has nothing to do with the moving frame or a rest frame. It just means that the proper time is for the frame for whom the events are happening at the same place. So example of this is, imagine there is a event 1 where a rocket leaves the earth, and event 2 is when the rocket reaches a Mars. Now from the earth's perspective, leaving earth and reaching Mars is happening at two different places. So earth will measure a dilated time. For the person in the rocket will measure a proper time, because if we imagine a person in the rocket, okay, the along with rocket the scale of the person is also moving, so he won't be able to recognize any difference in his distance or a scale. Okay, so we can see that the person in the rocket will say that I'm in the same rocket, I'm in the same place, earth went past by me and Mars went past by me, he just remained stationary. So For him, the events are happening at the same position as the scale is also moving with the person in the rocket. Okay, so that's the reason why the person in the rocket will measure proper time and the person on the Earth and Mars will measure a dilated time. This is it. Okay, the another similar example is the length contraction for relativity. So, like a proper time, there is a proper length as well. In a proper length, it is a length of an object measured by an observer for whom the object is at rest. It means that the table in front of you is at rest with respect to your plane. So whenever you measure the rate of this or length of this table, you will get a correct or accurate value. For the person who is moving at a certain velocity, the length measured will be contracted. Okay, so contracted length can be calculated by L naught over gamma factor. Okay, and it contract only in the direction of the motion. So if there is a cube of x, y, and z axis, it will only contract in the direction where the object is moving. Okay, and it won't contract in the direction which are perpendicular to it. We'll see an example of using proper time and length contraction. So in terms of muon decay, it's very famous experiment. In lab, muon is stationary and we measure the time for its decay and we could find its half-life. Now the proper time of muon decay, okay, uh, so half-life of muon decay will be proper time because when we held muon stationary, it means muon is stationary with respect to us and the events like creation and decay are going to happen at the same position because it is stationary held using some electromagnetic fields. And so muon's frame, according to muon's frame, the half-life of muon is 0.2 microseconds. So in the frame of lab or in the frame of muon. Okay. Then on Earth, the muons are created at the upper atmosphere due to all those cosmic rays, and they decay as they reach the ground. Okay. And so imagine the muons are coming down at the speed of 0.98 c. Okay, and the point where they are created is 3250 meters. Now, if we calculate the velocity of the muon, it will be 0.98 c, and for that, the gamma factor turns out to be 5. Okay. Now, time taken for muon to reach the ground. How much time it will take to reach the ground? It would be the distance over time. Here we won't use relativity. It is just because the distance is known as with respect to Earth. So this is with respect to the person on the ground. And even the 0.98 c is with respect to Earth. Okay. So the time taken for the muon to reach the ground will be 11 microseconds. That's true, according to the person on the ground. Okay. But if we apply the Galilean transformation, there is something wrong happens. So Galilean transformation, since the half-life is 2.2 microseconds, it means while reaching ground, 5 half-lives will pass for a muon who is going to come from upper atmosphere to the ground into 11 microseconds. In 11 microseconds, 2.2, 11 by 2.2 is 5 half-lives. 5 half-lives will be passed. Okay, and we can get the number, how the number changes from N0 to 2 in first half-life to N0 by 32. Okay, so only 3% of the muon should reach the bottom according to the Newtonian or Galilean transformations. Okay, now according to relativity, the half-life will be dilated for the person in the Earth because muon is moving. Okay, so the whatever 2.2 microsecond was the half-life measured during when the muon was stationary, but here the muon is moving, so the half-life we need to measure using gamma factor. Okay, so this will be dilated time, and dilated time turns out to be 11 microseconds. When we get the dilated half-life as 11 microseconds, it means that only according to relativity, only one half-life will pass while reaching the, okay, only one half-life will pass, and the number in one half-life will be only 50% of the original amount. It means that uh, according to relativity, more number of muons should reach the ground, and that is what exactly we found. Okay. So here, what was the important part in relativity? We consider that the time can be dilated. Okay, and we can also see that. Imagine there is a person on the muon, like observer on a muon, who is also moving at 0.98 c. Okay, the 3250, the distance is measured by the person on the Earth, how much high the upper atmosphere is. So for the observer on moving on muon, the distance between the ground and the upper atmosphere will be uh, contracted because it is moving at that speed. So how much will be the distance contracted? We can use a length contraction formula, and 3250 divided by the gamma factor is 5, and we get 650 meters as a contracted length. Now, according to the person on the muon, the time taken for the muon to reach the ground, okay, according to the observer on the muon, it will be 650 over 0.98 c, which gives us 2.2 microseconds. Okay, which is again one half life worth of uh, time, and same results come that 50% will reach the ground. So the relativity should go hand in hand. Here we saw length contraction, here we saw time dilation, both work. So for example, if for the Earth observer the time is dilated, then for the observer on the muon, the length would be contracted. That is something that we would like to remember. We'll see one more example of what is the proper length. Length measured by an object for whom the object is stationary. See, there is a train, there is a proper length of the train is 85 meter and the speed of the train is 0.8 c. Now, whenever you see your value, always try to see with respect to whom. This is relative to the stationary observer on the platform. Okay. In frame of reference, a ball travels from with a speed of 0.56 from the back to the front of the train, and as the train passes the platform, calculate the time for the ball to reach the front. So for the value of the length of the train, proper length of the train will be measured by the person in the train itself. The speed of the train, the speed of the ball, sorry, is measured by the person in the train. So for the person in the train, the ball speed is known according to him, the distance between the walls is known according to him. So he can calculate the this time interval by taking distance over speed. So distance over speed, if we take, so that would be 5.6 into 10 raised to minus 7. Okay. Now this was easy because all the variables are known with respect to the observer in the train. If you want to find the reference frame of platform, okay, since we know the distance in the reference frame of the train and we know the time in reference frame of the train, okay, we can use the formulas for transformation. So delta t is the transformation. So gamma times delta t dash plus delta x dash v over c square. And once we substitute all those values, we will get delta t is equal to 9.25 into 10 raised to minus 7. Okay. So here we clearly saw that we can use the time equation to get the value. Why we can't use time dilation formula? We can't use time dilation formula because events are not happening at the same position. Okay, for both observer, events are not happening at same position. Okay, only when the events are happening at same position we will see a time dilation. Okay, so ball is moving from back end to the front end is not at same position for both the observers. Okay, one last example we will quickly do. The two rockets A and B moving towards velocity of A is 0.6 c, velocity of B is 0.4 c. Okay, the Earth observer measures those speed according to Earth observer, and distance between them is 6 into 10 raised to 8. What is the frame of reference? As we already saw, according to observer, what is the time taken for A to meet? So let T be the time for both of them to meet. Okay, the distance covered by A is 0.6 ct. Basically, the distance from, let's say they meet somewhere here, the distance covered in this time is 0.6 ct, while the distance is 0.4 ct. Okay. Now, when we add this should be equal to 6. And once we do that, this should be equal to 6. So we will get time is equal to 2 seconds. Okay, so it will take 2 seconds for the A and B to meet. Now, if I want to calculate the velocity of B with respect to A, I will consider the velocity of this velocity as u, and we want velocity of with respect to A, so I will consider this as S dash frame and this frame as S frame. Okay, so we will get this part. We can substitute in this particular formula. Now here more important thing is 0.4 c. You have to take negative 0.4 c because the velocity is in negative direction. Okay, and we will get the velocity of B with respect to A is 2.4 into 10 raised to 8. For according to observer A, what is the time taken for B to meet? Now for observer A, the events are happening at the same place. So whatever time he measures is the proper time. For the Earth observer, it will be a dilated time. So we can calculate the dilated time, okay, by seeing that events are happening at the same position. Okay, for A, so A will measure proper time, Earth is measuring dilated time, so dilated time is equal to, proper time will be equal to dilated time over gamma factor, and 2 seconds is the dilated time according to the Earth. Gamma factor is 1.25, that is calculated using velocity of A, and we get 1.6 seconds. Okay, so this is how we can do relativity problems. Okay, thank you so much.